Till now, we've studied the general solutions of some random trigonometric equations which had the look, a trigonometric function equals a real constant, right? Now it's time to find the general solutions of similar looking equations, but the standard ones. You know, the ones that you will be encountering tons of times in your journey throughout trigonometry. The very first of such equations is sine theta equals 0. Agenda is to find all the possible real solutions of this equation. Well, I simply mean that we have to find all the real angles theta which satisfy this equation. You know, alternatively, I can say that we need to find the general solution of this very equation. And how exactly are we supposed to find it? Well, unit circle is the answer. We all are aware of the fact that for a point P sitting on the unit circle, sine theta corresponds to its y coordinate, right? This very y coordinate will be 0 on the x-axis, right? And we know the angles whose terminal ray coincides with the x-axis. What are they? 0, plus minus pi, plus minus 2 pi, plus minus 3 pi, and so on. Hence, extrapolating the same conclusion, we get that the value of sine theta will be 0 for angles such as 0, pi, minus pi, 2 pi, minus 2 pi, 3 pi, minus 3 pi, and so on. But if you carefully inspect the list of these angles, you will realize that they have one thing in common. What is it? Each one of them is an integral multiple of pi. And ta-da, we are done. All the integral multiples of pi are solutions of this equation. What is the equation? Sine theta equals 0, which means sine of an angle is 0 if and only if that angle is an integral multiple of pi. In other words, and you can take a note of this, the general solution of sine theta equals 0 is given by theta equals n pi, where n belongs to the set of all integers. With this, the first standard equation sine theta equals 0 is sorted. Now, let's twist things a little. What if we have 1 instead of 0 here? The equation now has become sine theta equals 1. Let us explore this case, okay? So, we'll draw the horizontal line y equals 1, and in the same Cartesian plane only, we will also draw the graph of the sine function. Once again, we can identify that the points of intersection of both these curves will give us the general solution of the equation sine theta equals 1. Cool then. What are these points? Well, this value right here is the angle pi by 2. We all know that already. Now, using the periodicity of the sine function, which is 2 pi, we can clearly see that the next value is going to be, yes, 2 pi plus pi by 2, which is 5 pi by 2. And the one after that is going to be 4 pi plus pi by 2, which is 9 pi by 2. And so on. This will keep on continuing. On the other side, we have minus 2 pi plus pi by 2, right? Which is nothing but minus 3 pi by 2. And then we have minus 4 pi plus pi by 2, which is simply minus 7 pi by 2, and so on. All of these values will satisfy the equation sine theta equals 1. Or we can say that sine theta will be equal to 1 if and only if theta is one of these angles. You know, if we wish to compactify this, then we will have to observe the general look of all these angles. What is it? Analyze very carefully. Take your time. Yes, each of these angles can be written as 4n plus 1 times pi by 2 for some integer n. You don't believe me? Let's check. Plug in n equals 0. What will you get? Pi by 2. Next, plug in n equals minus 1. What will you get? Minus 3 pi by 2. For n equals 1, we will get 5 pi by 2. Similarly, you keep on plugging in different integral values of n in this expression, and you will keep on generating the rest of the angles. So, this infinite set of angles can be in short represented as 4n plus 1 times pi by 2, where n varies over the set of all integers. Thus, the general solution of the equation sine theta equals 1 is nothing but theta equals 4n plus 1 times pi by 2, where n belongs to the set of integers. Done? Now, change this 1 to minus 1. A new equation we have, sine theta equals minus 1. Cool. So the task at hand is to find the general solution of this equation now. Once again, we have the equation of the form f of x equals g of x. No problem. We are already aware of the fact that the solutions of such an equation are given by all the x coordinates of the points of intersection of the two curves f and g. Right. So what are you waiting for? Draw the graphs of both f and g together in the same Cartesian plane. What next? Study their intersection points. It's quite evident that this point, sitting right here, is corresponding to the angle minus pi by 2. Right? We know that sine of minus pi by 2 is yes equal to minus 1. So definitely, minus pi by 2 is satisfying our equation. And that is why it is one of the solutions for sure. Now, once we have this, next we can use the periodicity feature of the sine function to find the remaining solutions of this equation. How exactly? See, sine is periodic with a period of 2 pi. Thus, we get 2 pi minus pi by 2, that is 3 pi by 2. Then we get 4 pi minus pi by 2, which is 7 pi by 2, and so on. Further, on the other side, we have minus 2 pi minus pi by 2, which is minus 5 pi by 2, and so on. So we get sine theta is equal to minus 1 if and only if theta is one of these angles. Now realize that each of these infinitely many angles can be written as 4n minus 1 times pi by 2 for some integer n. Convinced? Yes? Hence, this is their general look. Agreed? Thus, the general solution of this equation would be 4n minus 1 times pi by 2, where n belongs same set of all integers. Okay, done with sine. Let us now jump on to cos and play around with some cosine equations. The first one is cos theta equals 0. Now the drill to solve this equation remains exactly the same. Simply plot the graph of the cos function and find its intersection points with the line y equals 0. which is nothing but the x-axis only. Now, catch hold of the x coordinates corresponding to all these intersection points. What do you get? Minus pi by 2, plus pi by 2, minus 3 pi by 2, plus 3 pi by 2, minus 5 pi by 2, plus 5 pi by 2, and so on. So what are we getting? Cos theta is 0 if and only if theta is equal to one of these angles, any one. And the good news is that all these infinitely many angles have something very special in common. They are nothing but the odd integral multiples of pi by 2. Isn't it? That is why I can say that cos theta will be 0 if and only if theta is some odd integral multiple of pi by 2. Okay? And this we write as 2n plus 1 times pi by 2, where n varies over the set of all integers. In fact, you can visualize this even more easily on a unit circle. See, cos theta will be 0 only when the terminal ray of theta coincides either with the positive y-axis or with the negative y-axis. Isn't it? And this corresponds to what all angles? Yes, pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on in the anti-clockwise sense, obviously, and minus pi by 2, minus 3 pi by 2, minus 5 pi by 2, minus 7 pi by 2, and so on in the clockwise sense. Again, if you collect all of them, you will notice that they constitute the set of all the odd integral multiples of pi by 2. Right? And that is how the general solution of cos theta equals 0 is given by theta equals 2n plus 1 times pi by 2, where n belongs to the set of all integers. Wasn't this easy peasy? Now let's move ahead and examine the next equation, which is cos theta equals 1. Okay? And for this, we will simply plot the horizontal line y equals 1 along with the graph of the cos function. Here it is. Now, same exercise. Catch hold of the intersection points. Done. The angles corresponding to them are what? Let's read them out loud. 0, 2 pi, 4 pi, 6 pi, and so on. And then we have minus 2 pi, minus 4 pi, and so on. Right? The conclusion thus obtained is that cos theta will be equal to 1 if and only if theta is equal to any one of these angles. Okay? And these, by the way, are all the integral multiples of 2 pi. Agreed? Which you write as n times 2 pi or 2n pi, where n belongs to the set of all integers. Cool. This means that the general solution of the equation cos theta equals 1 is given by theta equals 2n pi, where n is varying over the set of all integers. Done? Now, instead of 1, let us quickly plug in minus 1. What happens in this situation? First of all, the equation now under observation becomes cos theta equals minus 1. See, we thoroughly know the steps, so just apply them one by one. Draw the horizontal line y equals minus 1. All right. And now capture its points of intersection with the graph of the cos function. Why? Because corresponding to these points of intersection only, we will get our required solutions. We know that already. See, cos is minus 1 at angles pi and minus pi. Taking help of the periodicity of the cos function, we can extend this to other angles as well, which are 3 pi, 5 pi, minus 3 pi, then minus 5 pi, and so on. The list is endless. These are the infinitely many angles whose cos ratio, by the way, is -1. But again, all these angles are nothing but odd integral multiples of pi. And if n denotes integers, then definitely 2n plus 1 will represent odd integers. You're right. Thus, the general solution of cos theta equals -1 will be given by theta equals 2n plus 1 times pi, where n belongs to the set of all integers. Okay, with this we are done with the sine and the cos functions. Now it's time to look at a standard equation consisting of the tan function. Consider the equation tan theta equals 0. Okay? Fortunately, we are well versed with the graphical procedure to solve this equation. Simply plot the graph of the tan function and now catch hold of its points of intersection with the line y equals 0, which is your x-axis only. You can easily identify that the angles corresponding to these intersection points are nothing but 0, pi, 2 pi, 3 pi, 4 pi, and so on. And on the negative side, we have minus pi, minus 2 pi, minus 3 pi, minus 4 pi, and so on. But wait, what are these angles? Can you decode something common among them? You know, any comments on the generalized look that they all are following? Think. Yes, all these angles are actually integral multiples of pi, which in the compact form can be written as n pi, where n varies over the set of all integers. That is how this particular infinite set of angles can be generalized as just theta equals n pi. So the conclusion is that the general solution of the equation tan theta equals 0 is coming out to be theta equals n pi for all integral values of n. Easy, right? With this, we have seen the general solutions of some of the most frequently used standard equations. Let us revise them quickly. See, first of all, recall that sine theta and tan theta both are equal to 0 for the same angles, which are what? Integral multiples of pi. Now, of course, graphically we have justified this, but you know what? There is another more intuitive explanation for both these equations to have the same general solution. What is it? Hear me out. See, tan is sine upon cos. And we have studied that sine and cos can never be simultaneously 0. What I mean is that for some angle, if sine is 0, then for the same angle, cos will not be 0. Okay, so tan of an angle will be 0 if and only if sine of that same angle is 0. Absorbed? But we have already proved that sine is 0 at all the integral multiples of pi. So, tan will also be 0 at each and every integral multiple of pi. Okay, I guess now you will never forget the general solution of both these equations. Next, we learnt cos theta is 0 for all the odd integral multiples of pi by 2. Then, sine theta gives 1 for theta equals 4n plus 1 times pi by 2. Right, and it gives -1 for 4n minus 1 times pi by 2. Further, cos theta has value 1 when theta becomes, yes, an even integral multiple of pi. And it has the value -1 when theta becomes an odd integral multiple of pi. You're right. That's all for now, folks. I hope the idea of principal solution and general solution is crystal clear to you. I'll see you soon.
Here's presenting the Aakash BYJU'S app for JEE and NEET. What are you waiting for? Hop onto the link down in the description box, download the app and get started. I'm sure you will have loads of fun. Happy learning.